Hello to everyone. My name is Kamariotis. I'm a PhD student in the Technical University of Munich, working with Professor Daniel Straub here in Munich and also with Professor Eleni Hadzi from ETH Zurich. And today I will give you my presentation for this online version of the YALCE 2020 conference. Our work related to this conference and also the title of today's presentation is about optimal maintenance decisions supported by structural health monitoring, a benchmark study. As all of you know very well, structures and infrastructure systems are subjected to adverse operational conditions, extreme events, aging, deterioration, etc. throughout their life cycle. Nowadays, sensor technologies have evolved astonishingly to the point that there are low-cost sensors available which are capable of reliably measuring different quantities of structural response, for example, accelerations, displacements, strains, temperatures, and so on. At the same time, the field of structural health monitoring has been developed in parallel over the last 3 to 4 decades. In one sentence, structural health monitoring deals with translating the raw measurement data from sensors into indicators of structural health. However, still, in the current approach to infrastructure operation and maintenance, visual inspection remains the primary means for condition-based assessment, and SHM systems have not been seamlessly transferred into extensive application on real-world structures. A question that still has to be answered is the following. What is the effect of SHM on optimal operation and maintenance, and hence on the total lifecycle cost? And what is the value of this information? We attempt in this presentation to investigate some answers to these questions. In this slide, I want to present to you a framework for a value of information from SHM analysis that has been initially suggested in a previous work in 2017 that we adapt and modify in this work, and then we apply it on an example. The setting is the following. Monitoring information can potentially be obtained prior to making decisions related to maintenance actions. But is it worth it? Well, pre-posterior Bayesian decision analysis provides a formal framework for quantifying the value of information of an SHM system prior to its installation. The figure on the right presents an influence diagram which models such a pre-posterior Bayesian decision analysis. Within our influence diagram, green colors indicate parameters and models related to the structure, orange colors are related to the SHM system and the SHM data, and red colors indicate maintenance and repair actions. The blue bubbles are the different analysis methods used in the different parts of the process, which will be presented in detail in the rest of the presentation. It is important to make clear that a pre-posterior Bayesian decision analysis is performed before any data is obtained and any actual system is deployed. Therefore, the potential monitoring data's histories must somehow be sampled. To demonstrate this framework I just presented, we decide to employ a benchmark numerical structural model. It is a configurable open-source finite element model which enables the extraction of dynamic response data at the assumed position of the sensors. In our case, we assume that there are 18 deployed accelerometers measuring vertical accelerations. This numerical model serves as a tool to create and sample the reference monitoring data from a deteriorating system over its lifespan. We parameterize the finite element model by some stochastic parameters theta, describing a deterioration model. For a given theta and for a realization of the Gaussian white noise excitation, we run a dynamic analysis of the model and we obtain the true acceleration time histories. To simulate a sensor noise, we add a Gaussian white noise error term to the obtained acceleration time series. Since we are dealing with a case of output-only measurements, we subsequently feed the noisy acceleration time series data to an output-only operational model analysis framework, and more specifically the stochastic subspace identification algorithm, with which we then identify the lower eigenfrequencies and mode-safe displacements. As mentioned in the previous slide, we need to employ a prior stochastic deterioration model, which describes the evolution of a sort of damage within the structure over its lifetime. Deterioration modeling can be extremely complex, and more often than not, the physics and the mechanics describing the deterioration mechanism are not available. For time-dependent reliability assessment purposes, simple empirical deterioration models can be adapted, like the one we describe here, So we employ a simple empirical model which reads t is equal a times t to the power of b, where parameters a and b are stochastic random variables driving the uncertainty within this deterioration model. Parameter a describes the deterioration rate and follows a log-normal distribution, while parameter b follows a normal distribution and it describes a nonlinearity effect in terms of a power law in time. The damage model that we employ describes a scour type of damage, and it explains how the stiffness of the spring, of the middle supported spring, is being reduced over the lifetime of the structure, with this parameter d describing this kind of stiffness reduction. I have just introduced the prior deterioration model that we employ here. Now we have monitoring data obtained sequentially at different time instances, and they can be used to set up a sequential Bayesian inverse problem. Our goal is the following. Every time new monitoring data becomes available, we want to estimate the filtering posterior distribution of the deterioration model parameters given all the data up to this time. Following Bayes' rule, the posterior distribution of the parameter vector theta given the monitoring data is proportional to the prior distribution multiplied with the likelihood function. The OMA identified model data are the lower M model eigenvalues and the mode-shaped vector components. The slide here is mainly focusing on the construction of the likelihood function. However, I will not explain it in detail. The likelihood function that we use here, with its equation written at the last line of this slide, is the state-of-the-art likelihood function that is used in works related to Bayesian model updating. In order to demonstrate how the sequential Bayesian model updating framework performs in identifying the parameters of the deterioration model, we assume the following scenario, that the underlying true deterioration model corresponds to parameter values A star and B star. We discretize the lifetime that we assume is 50 years into yearly intervals, and given A star and B star, given the true model, we create one set of SHM model data per year. For the solution of the Bayesian model updating problem, we employ an adaptive MCMC sampling algorithm. This slide shows some results of the sequential Bayesian updating. On the left side figures, on the top we plot in green the prior distribution of A and B, and in red the filtering distributions at year 30 and in the bottom at year 50. As can be seen, the uncertainty in the posterior distribution is reduced, only slightly though for parameter A and a lot for parameter B, and the posterior distributions are centered around the true values of A star and B star for which the data was created. On the right-hand side figures, we plot the deterioration model evolution over time, once on the upper left using samples from the prior model, and in the rest of the figures using posterior filtering MCMC samples at 3 different time instances. The monitoring data from initial years, here we are at year 10, do not prove to be rather informative because deterioration is a slow process, while if we look at the posterior predictive models using data up to year 30 or even up to year 50, we observe that we are able to identify the deterioration model evolution and significantly reduce the uncertainty in this estimation. The details related to the modeling choices and how the reliability analysis is performed in this work will not be given in this presentation, and the interested reader can find the details in our conference paper. In this slide, we are only showing some results. The green curve on the left corresponds to the accumulated probability of failure curve in the prior case using Monte Carlo samples from the prior model, while the red curve is the updated accumulated probability of failure curve conditional on monitoring data created for A star and B star. For the red curve, we are using samples for all the intermediate posterior filtering distributions. On the right-hand side, we are plotting the hazard function curve in the prior and posterior cases. In this figure, we are also including the credible intervals in the graphs to show an estimate of the uncertainty, and it is clearly seen how less the uncertainties in the posterior case compared to the prior case, given the monitoring data. Let's now briefly look at how we approach the solution to the lifecycle optimization problem. To do that, we employ a heuristic-based approach. We have a decision time horizon of 50 years, which corresponds to the lifetime of the structure, and we discretize it into yearly intervals. We assume that we have the option between two actions, either to do nothing or to perform a repair action, which we model as replacing the structure and bringing it back to its initial state. We need to assign some values for the cost of the repair action and the cost of the failure event. The heuristic that we employ for solving the decision problem is the following. We perform a repair action at the time step for which the hazard rate exceeds a predefined heuristic threshold W. Then, the approximate solution to the decision problem boils down to solving the optimization problem that you can see at the end of this slide. And we want to find the optimal heuristic threshold, which minimizes the expected total cost of maintenance and risk. The expectation operator that appears within the stochastic optimization problem differs between prior and pre-posterior case. In the prior case, the expectation operates over the system state theta, which is the deterioration model parameters. This integral can be solved with Monte Carlo simulation. In the pre-posterior case, the expectation operates over both the system state theta and the sampled monitoring data z. This is computed by jointly sampling theta and z via a crude Monte Carlo simulation. Finally, after solving the corresponding optimization problems, we have computed the optimal expected total lifecycle cost in the prior case and in the pre-posterior case. The value of information is the difference between the two. This slide is a summary slide and is related to the algorithm for computing the value of information in this case. So we obtain samples theta from the prior deterioration model and we separate between prior and pre-posterior case. In the prior case, using these prior theta samples, we compute our reliability curves, our lifetime probability of failure and hazard function. We solve the lifecycle optimization problem to obtain the optimal heuristic threshold and the time to perform the repair. And these define our optimal expected lifecycle cost in the prior case. In the pre-posterior case, for each sample of theta, we need to sample the corresponding lifetime monitoring data. For this data, we perform a sequential Bayesian model updating to obtain the filtering posterior distributions of theta. And using the obtained posterior MCMC samples, we estimate the updated lifetime reliability curves. We solve the lifecycle optimization problem for this specific deterioration monitoring data realization. And in the end, after we do it for all the samples, we need to average over the posterior optimal solutions to obtain the optimal expected lifecycle cost in the pre-posterior case. Our value of information is the difference between the two optimal solutions in prior case and pre-posterior case. We have now reached the results section, and I will first show the results of the heuristic-based lifecycle optimization problem in the prior case, which we obtain using 500 Monte Carlo samples from the prior model. We need to define some costs. So for the cost of the failure event, we define rather arbitrarily here a value of 10 to the power of 6 units. And for the cost of repair, we assume different ratios in relation to the cost of failure. The second column here shows the optimal heuristic threshold for each of those problems for the different cost ratios, while the third column shows the optimal expected total lifecycle cost given the optimal value of the heuristic threshold. Finally, the fourth column here shows the optimal time to perform a repair action. And as you can see, in the first three cost ratio cases, not performing a repair is the optimal thing to do throughout the lifetime of the structure, while for the last cost ratio, the optimal action is to perform a repair at year 31. In the pre-posterior case, we use the same 500 Monte Carlo samples from the prior model, but in this case, for each theta sample, we create a monitoring data history and we solve many different lifecycle optimization problems. The cost of failure is the same and the same cost ratios. And as you see here, In this table, we do not give the optimal time of repair, since in the pre-posterior case, the time of repair is varying for each sample and monitoring history. So we are showing the optimal heuristic thresholds and also the optimal expected total life cycle cost given the optimal heuristic threshold in the pre-posterior case. Finally, bringing everything together, we saw the VOI results for each of the assumed cost ratios. When the cost ratio is 0.1, the value of information assumes a value of 0, which means that one does not obtain any benefit from the SHM data. This is related to the fact that for this cost ratio, the optimal action in both pre-posterior and prior case is to not perform any repair action throughout the lifetime of the structure. However, for the further considered cost ratios, the value of information is positive, which indicates a potential benefit of installing an SHM system on a deteriorating bridge structure. Finally, this slide concludes this presentation. We have presented a realistic pre-posterior Bayesian decision analysis framework to quantify the value of information from SHM systems, which for the first time attempts to model the entire SHM process. To the best of our knowledge, is the first time that Bayesian model updating with dynamic data is implemented within a VOI analysis, and we have employed a simple numerical benchmark of a bridge-type deteriorating structure, and we have applied our VOI analysis framework. These are my references. We would finally like to acknowledge the TUM Institute for Advanced Study for their support in this project.